Now it's my great pleasure, we've got a special treat for all of us here this morning to introduce our first keynote speaker for Quantum World Congress 2023. Dr. Peter Highnam is the Chief Strategy Officer in the Office of the Undersecretary of Defense for Research and Engineering, and he's the Principal Deputy Assistant Secretary of Defense for the Office of the Assistant Secretary for Defense for Critical Technologies. Prior to this role, Dr. Highnam was the Deputy Director at DARPA, and he also served as the Acting Director at DARPA twice. Dr. Highnam also served as the Director of Research at the National Geospatial Intelligence Agency, NGA, and served as the Director of IARPA and as a Senior Advisor to the National Institutes of Health, NIH as we call them here. Dr. Highnam holds a Doctorate of Philosophy and Computer Science from Carnegie Mellon and a Master of Science in Mathematical Logic and Foundations of Math from the University of Bristol in the UK, Bachelor of Science in Computer Science from the University of Manchester. So, ladies and gentlemen, please extend a warm welcome to Dr. Peter Highnam. A very warm welcome to Dr. Peter Highnam. Thank you. Thank you.
Okay, so thank you for the introduction. So what I'm going to do, let's see, get past this, oops. Okay, is review findings from a quantum science roadmap that was produced by Dr. John Burke, working inside our R&E Research and Engineering enterprise. The bottom line is, we're advancing and applying quantum science to make a difference. We are defense, we have specific interests. They have commercial overlap, of course. We depend on companies. But the way that we evaluate, the way that we look to prove and move out technologies is a little different, and I'll explain. I want to thank to the organizers for this, and really encouraging to see the international participation. I'm going to begin with some notes on commercial background. So I'm going to make some comments as I go through, and I want to explain a little bit, or give a little backdrop for that. So after grad school, I worked for an oil and gas exploration company for about 12 years. And one of the things I discovered, this was back in the 90s, was quantum science in use for field measurements, as in gravity measurements down inside a borehole. And so a long way down, superconducting temperatures. It's a very hot, very rugged, robust environment. And once I found out what these folk, the engineers and scientists in the company were doing, I was in awe, because I never imagined that you could do something like that and make that kind of measurement and have customers for the results. I'll come back to that too. Now, I was hired by that company, yes, to work with data that was coming off sensors, but also to replace what back then were craze. Large vector systems, XMPs, YMPs, for those who were in the game back then, because the new thing that was coming online were these massively parallel processors. And the way we got advantage from these new machines, massive cost advantages, performance advantages, was by going back and revisiting the math and the physics that we'd taken for granted and crafted and honed to work on the big vector systems. Both of these points, you'll see how I'm informed in some of my comments as we go through this. I also, from I've done 2 tours at DARPA. The first tour was as an electronic warfare program manager, and that's where I really learned the value of clocks. I'll come back to that too. Let's see. Thank you. Now, research and engineering, Ms. Heidi Shu serves as the CTO for the Department of Defense. And that's a tough job, as you can imagine, a very important job. And there are so many, but every area of technology, in some sense, is important to the mission. But within within that vast remit, there's a set of 14 that have been called out and as to be the critical technology areas. And I want to point out for this meeting that quantum science is absolutely one of those. And I'll give you examples coming up of things that go on. Now, as you look through this list, it's pretty clear, right, that these are not clean silos. So we're looking at AI and microelectronics. Is anything on here not touched by those? And vice versa, AI systems requires high-end microelectronics. Microelectronics design requires AI. And as quantum science moves ahead, and I'll give examples, it shows up in other places, and of course, it's used, requires advances in other places, specifically with examples coming in the microelectronic space. I'll also note that I have some involvement with AUKUS, and in Pillar 2, we actually have an active quantum science operation. Now I'm going to talk about how we, from a military perspective, look at the advances in quantum. There we go. So the measurement for us is readiness from a military perspective. So this is Department of Defense. So top on the left is the potential military impact. To the bottom, military readiness. Colors, again, the green is approximately devices, where the major issue is CSWAP, cost, size, weight, power. And the others are things that tend to be immobile or less portable and have other uses. I'm not going to get into the details and the eaches of this, but to point out that looking at the cluster up on the top right, those are results of device technology investments over more than 2 decades. They're now being matured. Again, cost, size, weight, and power are foci, and I'll come back to that. A specific example is DARPA's chip-scale atomic clock, which was about 2 decades ago. Today is available in approximately about 16 cubic centimeter package, and is about a microsecond over 8 hours in terms of stability. It's still not where we need it. And we have research and engineering, manufacturing technology investments underway now to get where we need to get to. I'm also going to point out here that when we talk about clocks, when we talk about sensors, we're talking about position, navigation, and time. And again, you'll see more of that coming up. Now, how do we structure our efforts? Next slide, please. These are the strategic bins, and I'm going to go through with examples each one of these. The quantum technology first. PNT, precision, navigation, and timing. For those of you who track this particular area, going back to the 18th century in the UK, there was a prize challenge called longitude, because there had been some military disasters, Navy disasters going to the wrong place. And the issue became, how do you measure longitude at sea robustly? The winner was a clock company, a clock maker called Harrison. And the story, I'd like to say, is going into a ton of details in there, of course. But come forward to today, how do we do PNT? Well, we use clocks. GPS is based on good clocks. The better the clocks, the better the PNT. Then when you add into that, in PNT here, the notion of gravimetry, mobile gravimetry, magnetometers, and so on, there's a lot of effort, a lot of push, a lot of need in PNT customers. On the compute front, under quantum technology, what I'm going to explain at the moment is, in our assessment, there's work to be done. Quantum science, it's a rich, fascinating space. This is to the left. So much needs to be done. It's a really vibrant ecosystem of researchers working that. A lot of investment going in, everything from basic processes, How do you harness entanglement at a distance? Distance is large enough to be really useful. This whole zoo of different qubit technologies still exists. And then quantum engineering to the right, we make exotic demands of hardware for this field that we don't necessarily make for other places. So cryogenic temperatures, diverse materials, operating sometimes in vacuums, a lot of environmental isolation required. The good news is that there are advances going on in the engineering front, and there are commonalities across the quantum technology. So advances in sensors, advances in clocks, components 4, also support advances in other areas, including compute. Last, but by no means least, a quantum workforce. Quality in terms of backgrounds, skill sets, approaches. A lot of people here are working to make sure that we have that mix. It's absolutely required. And must be multidisciplinary. I'm sure that we've all heard the stories about the compute guys. I am one, or I used to be, so I can say this. Go in a corner and solve a problem and do really well, and it's not the right problem, which is back to where we measure performance in terms of military effectiveness. That is where the rubber meets the road. We have to have the physicists and the compute people, or the chemists, the people working the real applications, working together to solve problems and do it creatively. And this is why I hark back to my first comment about working to replace craze with something else, because that was going back to the original math and science with the experts in those fields and reimagining, reinventing the applications. Next, please. Now, a specific priority that we are working is in the area of sensors and clocks. So I mentioned that a lot of this is mature or maturing. What we're now doing is finishing that, pushing that harder and faster to mature and to field devices. So here's a range of sensors and clocks. Strategic priority for us: cost, size, weight, and power, ruggedization. It's a national quantum initiative priority. It's a DoD priority. And a research and engineering push is planned, a real hard push is planned beginning 2024. So this is just really good news. Quantum engineering is the focus of this area of work. Now, next, please. Now take a look at compute. Bottom line is perhaps that one-liner from the London Underground is mind the gap. This isn't as clear. So from Feynman's original idea back in 1981, there's been a ton of work. Personally, watching the hardware go through, that's looking from IARPA, working at DARPA. So IARPA, MQCO, CSQ, Logic, DARPA, ONISQ, US2QC, and many other programs in other places going after the hardware, the things to the left. And we will need to get quantum error correction or things that fault-tolerant QC to a good place at scale to go after applications that really are of interest. And this is where we need the customers in both the commercial sense, but also in for us, the military sense, with real applications to say this is now big enough, or this is now has the right properties, or can be used with classical compute in the right way to achieve the results that we need. I'm particularly watching things like DARPA's quantum benchmarking program for DoD relevant applications, which goes everything from fuel design, perhaps, up to optimization and other things. A lot of different spaces to play, and a lot of analysis needs to be done. And there's a sense that much of it is tied to specific potential architectures. So it's still a broad push. So mind the gap is there. This is where the creativity of the workforce, so recasting and reimagining input problems onto this weird hardware is absolutely required. Meantime, of course, classical isn't standing still. we have CMOS advancing, we have 3D heterogeneous integration moving past the end of Moore's law, all really important. And then programs like DARPA's quantum-inspired classical computing, which is reinventing or reimagining or going after those hard problems again, but now inspired by the analysis being done to support quantum systems. So the threshold goes up every time. A lot of work to do. Important, lots of work to do. Next, please. Another priority. Looking at the industry base, this is now quantum engineering. Won't go through all the components and things here. These are just examples from the quantum science roadmap. But what we have to do is we need very high performance, very exquisite properties. At the moment, niche markets and technologies, so cryogenics. How do you work in that space is expensive. How do you engineer to work there? How do you get creative? How do you get a lot of different people and systems being engineered to work and operate there? The good news, one, that it's a DoD priority to address this. And there's much overlap with the sensors and clocks work, the maturation and fielding that we're going on, where we do have application pull, and that strong sense markets exist. We know what we can do. We know what we need to do. It's a question of getting the gear into the right form factors and cost points to do its job. And second, I want to talk about a little bit about the Department of Defense's microelectronics commons and the tools and infrastructure that are being brought to help. Next, please. So announced last week were 8 awards rather, to what are called hubs in the microelectronics commons. This is an activity, the commons is on the order of $400 million US a year. We have 8 hubs. There will be projects executing in those hubs. And what I'm going to do is explain how the relevance to y'all. So first, when we put out the request for proposals, we said there are 6 areas of real interest to the department. And those are listed as up in the green section in the middle, one of which is quantum technology. And so when people then bid to us, we said, okay, tell us about the strength that you're bringing, the tools that you're bringing, the specific hardware elements, the software that you're bringing or think you could bring, the people, the bench, not just from one facility, but from a network of facilities that you make with partners. And the objective is not to do basic research here. This is not a quantum science activity. This is 6-4, government speak, 6-4 and up for those who speak that language. But this is really application. You've made something work in your lab, in a small business, or a large business, or a school, and now you want to see what else has to be done to take this through to a form where it can be manufactured at scale in commercial foundries. That's where we're focused. And again, 8 awards, 8 regional hubs were announced last week by the Deputy Secretary of Defense. And of those, a good number in their proposals claim and were assessed to have expertise that can really help with the job. So we're not just investing directly with the previous work I described in terms of maturing and fielding. We're going out to the quantum science community, the people who produce things now. How do I make my new invention? How do I make it real? How do I scale it up? How do I make it commercial? Dual use is fine. And that's what this is about. Infrastructure in terms of physical technology, software, people, and expertise. And all the hubs have also a mandate to improve the workforce, the overall workforce, not just within their own networks, but also more generally. So there's a lot of opportunity here. Last thing I should point out from this is one of the first major awards that came from the CHIPS and Science Act passed last year. And we're expecting, now that the hubs are announced, we're expecting project proposals or requests for project proposals from the hubs to go out early in the fall. Next slide, please. Lastly, huge thanks to everybody working in this area. It's incredibly important. Again, some real wins over decades. So much more is possible. Now we're figuring out what we can do affordably, and where we can do it. So position, navigation, and timing, sensors. There is, for the exquisite needs that we have, that has to be the future. That fundamental research, that, I would make a quantum joke here, but that the foam that's enlivening everything else, that's a constant push of new ideas coming into this whole ecosystem. Quantum computing, again, I'm a compute guy, and has work to do. Mind the gap was the one-liner I used there. The industry base. There's a lot of needs, common needs among quantum engineering, across quantum tech, across the commons. A lot of investments are being made. Pretty optimistic that we're going to see some big wins, because a lot of stuff now becomes possible. And for those who work in engineering and product, it's when you change that language, oh, I don't know if I can use this. Well, now you can. So what else can I do based on that? So I think there's some real acceleration going to happen. Workforce availability, it's a challenge being addressed by a lot of initiatives, as some discussed here. It takes a while to turn that around. And we're pushing too, and working as hard as we can to make things succeed. So I want to thank you for what you do, for coming to these types of events, to ensuring that this ecosystem keeps moving. I'm in defense, so my needs are very specific. I know what I need for the warfighter, and there's a lot of stuff I know I don't know yet as well. So looking forward to being pleasantly surprised at any time. And this is truly an exciting field to be in today. So thank you.